All right. Any questions? All right. So last time we discussed the Zariski tangent space of a scheme, which just means I take my maximal ideal in the local ring, I divide it by its square. That would be the cotangent space. I have to dualize this, and I'm dualizing this as a of P vector space. All right, and an important invariant to look at is the dimension of this guy as a vector space over K. Interesting. I can put the dual, but the dual doesn't actually matter as a function of P. Certainly not always, because there are, horrible schemes like, for example, if you took spec of polynomials and infinitely many variables. So there certainly are, you can easily cook up ones where this space is infinite dimensional. But of course, if X is, let's say, locally finite type over a field, then no, it has to be finite dimensional. So in practice, usually finite. All right. And in fact, so now assume that is locally finite over a field. Oh, yeah. I'm getting ahead of myself. Okay, great. Oh, yeah, over a field. Then we can check again that this is this dimension is low, wait, no, upper semi-continuous. And I don't think this is really absolutely strictly necessary, but we so rarely think, and particularly this does avoid any appearances of infinity. And in general, these sort of operations behave a bit better if you're locally finite type over a field. Hmm? Oh, sorry, locally finite type, yes. It's locally finite over a field wouldn't be that interesting. It would be true, but no. Whereas, finite type is a relatively small sacrifice to make. An image is a discrete set. Yes, this usually happens. No, that's exactly where semi-continuous comes in. It means you can jump up but not down. So there will be points where it jumps upwards, but it never jumps downwards. So for example, let's look at c of xy mod x squared minus y cubed. So all the points in here are of the form a squared a cubed, or a and c. All the closed points, I should say. There's also the generic point, but let's not worry about that yet. And particularly the generic point is going to be 0 field, so this is just 0. If a is not equal to 0, then you can check the Zariski tangent space at this point is a copy of C. Whereas if a is equal to 0, then this Zariski tangent space is 2-dimensional. So this is sort of a very common one. After this is telling me that y has to be positive. So did I do the equation where it's this guy, or did I do the flipped one? That's this guy. So at most points, I get a nice smooth tangent line. And then at this point, something goes wrong. Obviously, I look at this and I say, well, I'm not going to have a well-defined tangent line. So what algebraic geometry always does is it says, well, I throw in anything that might be a tangent. Right? Exactly what's happening here is, right, if I think about this parametrization, I'm sort of traveling down, and then as I come here, I slow my speed down to 0. And so the velocity vector here is 0. And what's my cotangent space? Well, in this case, it's going to be all the stuff which vanishes on the velocity vector. Right? I get a 2-dimensional space of sort of first order bits of functions, all of which are kind of compatible with restricting to this curve, whereas at a generic point, right, I genuinely get a restriction on what kind of directional derivatives I can take. One way to think about this is I think about a point and a vector at that point, and I ask, is the directional derivative with respect to this vector, does it only depend on the restriction of my function to this curve? Right? Will I get a non-zero answer when I apply it to an element of this ideal? And if I'm at a smooth point of this curve and I point off of the curve, then this guy has non-zero partial derivative. And I see, oh, I can't get a well-defined partial derivative in this direction for functions on this curve. I can only get a well-defined partial derivative if I look at the tangent direction. Whereas here, at the origin, any vector will give me a well-defined directional derivative for functions on the curve. Okay. So how did I know that? Well, what was I using? What I was using is that this is a critical point of the function x squared minus y cubed, whereas these guys are not. If I change this to be x squared minus y cubed minus a, right, then I would get a nice smooth curve here. It would sort of smooth this guy out. Or I shouldn't have used a there as my parameter. And I haven't actually graphed what this looks like, but it's some sort of, you take this guy and you sort of smooth out the king. All right, cool. So this is pointing us to a more general way of thinking about whether points on affine varieties of finite type over a field are smooth. So if x is equal to spec of k of x1 up through k of xn mod 1 up through fk, then I'm interested in when I take a point of this, is that point going to be sorry, didn't make an important definition. That was silly of me. Noticed that I hadn't, and I went back to do it, and I think I just got sidetracked. Okay. So this is an important number, and there's a general theorem that that's never less than the Kroll dimension of the local ring. So theorem, let R be a local ring. Then the Kroll dimension of R is less than or equal to the dimension of the maximal ideal mod the maximal ideal squared. And this is the dimension over the residue field. And once you know the proof of Kroll's theorem, the proof of this is actually pretty easy. I won't go through all the details, but the idea is that I take an element of M, which isn't an M squared, and I look at R mod F. Right? And Kroll's theorem tells me that the Kroll dimension of this is greater than or equal to the Kroll dimension R minus 1. And on the other hand, I kill one element of this vector space. I just do induction. Oh, and I should have, again, it's in my notes, Noetherian. And part of what I'm using Noetherian for there is a Noetherian local ring is finite dimension. Yeah, it's finite Kroll dimension. The examples of Noetherian rings that have infinite Kroll dimension come from kind of hooking up a big sequence of maximal ideals where the localization at that maximal ideal is a Noetherian local ring of finite but growing dimensions as you go through the different maximal ideals. Okay, cool. So a particularly interesting case is when this inequality becomes an equality. Well, definition, R is regular if the Kroll dimension of R is equal to the dimension of maximal ideal mod the maximal ideal squared. And you should think of this as sort of a smoothness property. So unfortunately, there is a technical definition of smooth, which isn't quite the same as this. We'll get to that in a moment. But the regularity comes from the idea, it was another word for being smooth. So this is sort of measuring, does something bad happen at the special point, which is different from the generic behavior? Right, so in this example, if we take this guy, which is the same, of course, as C adjoin T squared, T cubed, I identify T squared with Y and T cubed with X. So if I look at this guy and then look at its local ring for the maximal ideal, I want to write T here, but of course I should say T squared, T cubed. So this is the local ideal corresponding to the origin. then, well, if I'm going to be in the square of the maximal ideal here, that's going to be generated by T4, T to the 5, T to the 6, right? If I want to be in the square of the maximal ideal, the smallest power I could get is 4. So T2 and T3 are independent mod the square of the maximal ideal, which here is X and Y are independent mod the square of the maximal ideal. Yes, right. This is a property of local rings. Now we say that a point P in a scheme X is regular if its local ring is a regular local ring. This is a property of local rings, but any property of local rings, you can always transfer over to points of schemes by saying that that point has the property if the local ring at the point has that property. And this is only a property, well, so more generally, so we would also call any ring is regular. This is again a definition. If RP is regular for all primes. And then finally, right, I told you what it means for a point in a scheme to be regular. So X is regular if all of its points are regular. So in contrast to this, we say B is singular if it's not regular. So this property, this is sort of the algebraic geometry equivalent of being a math. Right? And so being a singular point is sort of a point where you fail to be a manifold. For example, here, this point is singular. All the other points are regular, including the generic point. Right? One thing you can immediately see here is the generic point of a smooth scheme, of an integral scheme is always regular because the stalk at that point is just the fraction field. There's no Zariski tangent space. On the other hand, I could have a scheme that was irreducible and not reduced and have a non-trivial Zariski tangent space at the generic point. So, spec of C of epsilon mod epsilon squared is an example of that. That's a scheme with one point. It's irreducible. Its generic point is the only point it has, but it has non-trivial tangent space there. It has a one-dimensional tangent space at its only point, which is also its generic. All right. Any questions? All right, so what I was getting to here and got slightly sidetracked from is how do you test this? How do you figure this out? Well, this assumes that you know how to check what the dimensions of schemes is. The dimensions of schemes are. But there's a very useful version of this, which is what's called the Jacobian criterion, which is just a generalization of the observation we made here, right? The problem here was that it was a critical point. So let X be spec of a field, actually 1 up through N, 1 up through Fk. All right, so the way I want to think about this is I'm taking AN over K, right? And I'm mapping that to AK. Oh, I probably shouldn't use K, should I? Okay, fine, I'll use R. AR over K, right, by the map F1 up through K. Okay, if we were in a manifolds course, right, what would I tell you? I would tell you that a regular fiber of this map, where the Jacobian has full rank at every point, is a manifold. So now I'm going to tell you the same thing is true in algebraic geometry, but you have to say regular instead of a manifold. And you have to be a little bit careful about what point means. So if P in X, so right, X is a subscheme of AN, is a K rational point. So what does K rational mean? It means that KP is equal to K. So if I were algebraically closed, that would be automatic. If I'm not algebraically closed, I have to be a little bit more careful. E is regular. If and only if the Jacobian at that point has full rank. So let's call I wrote the Jacobian somewhere. Mostly just I want to make sure I get my Jacobian transpose and I don't transpose things. So J is the partial derivatives do N BDFR BDX1 BF X as rank R. All right, so what is this? Well, let me say if there's going to be dumb stuff about like, what if the derivative wasn't surjective? So let me just say if. I'll try to make it difficult. All right, cool. So why is this? Like, why is this guy showing up at all? Right? I think the biggest mystery here is what the heck is going on with this guy? Well, the reason is, of course, we have a map of tangent spaces. So since P is in X, it maps to 0 in AR. So I'm taking the tangent space of AN at a point. I'm taking the tangent space of AR at a point. What is this map? So we would often call this P of F, right? And again, in differential geometry, I would say something about pushing forward curves and looking at the velocity vectors of those curves or something. But of course, in algebraic geometry, what I have is pulling back functions. So because I have a local homomorphism, I can look at the maximal ideal of 0 in the local ring in AR, and that maps to the maximal ideal of P inside AN, right? And then this maps down to the cotangent space of AR at that point. That maps to EPN. And if you think about what this map is, so it might be really weird that I put partial derivatives here at all, but this is sort of purely formal, right? You know how to take the partial derivative of a polynomial, and you just say, well, Newton quotients don't make any sense, but that formula for how to take the partial derivative of a polynomial makes sense. And the reason that's relevant is, right, Laurent it's true that Laurent expanded. Taylor expansion of polynomials is still true with that definition of derivative. So you sort of do that formally. That tells you, like, how does your polynomial Taylor expand at that point, even though there's no analysis justifying what's going on? It's purely algebra, right? It's basically just the binomial theorem. All right, which is to say, this map on cotangent spaces, right, it pulls things back. And so it's given by either this matrix or the transpose of this matrix. It's given by this matrix. So this is the matrix of this pullback map. So the transpose of the Jacobian is the push forward map. Okay. All right, cool. So in general, what's true is that the dimension of the tangent space at this point to X is the co-rank of the Jacobian transpose, i.e., it's the dimension of TPAN mod the image of J transpose. So in this case, it's sort of very dumb, right? What is this matrix? Well, I only have one F and I have two variables. So when I calculate the Jacobian, I take the partial derivative with respect to X and I get 2X. I take the partial derivative with respect to Y and I get 3Y squared. And I get a one-dimensional Zariski tangent space if this vector is not 0. And I get a two-dimensional one by the co-rank if it is 0, if I'm at the origin. All right, so that immediately tells me this observation here that this fiber has one singular point at 0, and every other fiber is smooth because there are no other critical points. All right. Any questions? Yeah. No. It comes from the Taylor expansion, right? So it's not that the second derivatives lie in the vanishing set. It's that the second derivatives, when you write them in the Taylor expansion, are times guys that are in the square of the maximal ideal, right? So where this comes from is if I have some function, I want to expand it at this point, I have a general f of x that's equal to f of p plus square of ddf ddxi, xi minus p, but I'm doing this on an, right? Psi minus pi. And of course, these are evaluated at p, right? And then plus sum over, yeah, is that what I want? I have to think a moment about getting I might be off by a constant here or something just because I didn't prepare this, but right. Then I get the partial derivatives with respect to I and j. And what do I get here? I get xi minus pi times xj minus pj, right? And the important point is this is in m squared, right? So that's why you pick this up. If f were in the ideal, this term would be 0. And so exactly what I was mod f squared would be given by these coefficients. And that also tells you that, if these coefficients are not 0, I need to check that this is not an m squared. Now we're talking about calculating the Zariski tangent space of an, right? EP n is equal to k to the n if he is a rational. And exactly what you find here, right, is that if something has non-zero partial derivative with respect to any of the variables, it can't lie in the square of the maximal ideal because of the Leibniz rule. All right. I won't prove this since it's a little harder when you want to take into account non-rational points, but is regular for all k. And actually, more generally, I could put any smooth. Let me not make a more general statement there, right? There is a sort of weird subtlety, which I hesitate to even mention because it's so subtle and so unlikely to come up anywhere in your real life. But it is just worth mentioning since you'll see both words. So being regular is an absolute property of a scheme, right? A scheme is regular or it's not. It has some singular point somewhere or it doesn't. Whereas this notion of being smooth has something to do with being finite type over a field, right? So we say that x is smooth over k if it is locally isomorphic as a k scheme to exactly a quotient like this, where the corank of the Jacobian doesn't jump, is equal to the dimension of the local ring sorry. Yes. Um, so being smooth is a relative notion. And just for time, I won't go into the details of it, but you can sort of guess how I would extend this to a general notion of I have a map from X to Y, which is smooth. So smooth things are always regular, but you have to be a tiny bit careful. Smooth implies regular. But there exist regular things in characteristic P which aren't smooth. So smooth actually comes up a lot more because, for example, it behaves well with respect to base change, right? So you should think of a smooth map as being one where the fibers are all smooth and they kind of vary in a smooth way, the way you would expect a submersion to behave in differential geometry. And in characteristic P, there's sort of some weird things that can happen because, right, if I'm in characteristic 0, a polynomial is not 0 if and only if um, you, you have to actually be a tiny bit careful about the statement I was making about this Taylor series thing, because there are some over 2's that show up, right? So I was being a little cavalier here. This thing about the partial derivative still works in characteristic P, but if you were to write down this formula carefully, there would be some over 2's here. And you would say, oh, actually, this formula doesn't work in general in characteristic 2. And then if you went to third derivatives, wouldn't work in characteristic 3. So there's some weird stuff that arises from the fact that if I'm in characteristic P, if I take X to the P and take its derivative, I get 0. Right, so this is a non-zero polynomial whose derivative vanishes everywhere, which can't happen in characteristic 0, but it can happen in characteristic P. So there's a lot of kind of issues that come with that, where you have to say things are separable, blah, blah, blah. So this is mostly just to warn you, you do have to be a tiny bit careful about the difference between smooth and regular, but only in characteristic P, and almost always you'd prove something is regular by proving that it's smooth over phi. Or, smooth, more generally, has a smooth map to something that's already regular. All right. Oh my God, so little time left. All right, so regular local rings have a lot of very nice properties. So for example, they're automatically reduced domains. Local rings. Even better than that, they're actually always UFDs, unique factorization domains. And so in particular domains. So connected regular scheme is integral. All right, in particular, even if it's not connected, it would always be reduced. All right. The most important special case of this is when the dimension is 1. So in that case, regular local rings have a special name. Which are called DVRs, discrete valuation rings. And there are an enormous number of characterizations of these. So the following are equivalent to being a regular local ring of dimension 1. So say for our Noetherian of dimension 1. Regular, the maximal ideal is principal, right? By Nakayama's lemma, this quotient m mod m squared is also the minimal number of generators of the maximal ideal as an ideal. So if it's 1, that means the maximal ideal is principal. R is integrally closed. So sort of the only way that a one-dimensional Noetherian ring can, a local ring, can fail to be regular is it can fail to be integrally closed. Right? And we saw this example of C of xy mod x squared minus y cubed. That's kind of the canonical example of a ring which isn't integrally closed, right? You can think of it as the ring generated by t squared and t cubed. Well, t is in the integral closure, and I kind of intentionally left it out. All ideals in R are of the form take the maximal ideal and raise it to a power, or of course, since it's a domain, there's also 0. No, not even just because it's a domain. But also add here that this will happen if and only if R is a PID, if and only if R is a UFD. And the last, kind of most important one of these is where the name discrete valuation ring comes from. So the final thing that you get is if I look at the fraction field of R, that has a map to the integers called nu, which satisfies what are called the valuation properties. So if I take nu of x plus y, I get the minimum. Oh, let me say non-zero elements of this ring. I get nu of x, the minimum of nu of x and nu of y. And if I take the product, I get the sum. And these look a little random, though you've seen them if you've taken a commutative algebra course, I hope. These are the rules that vanishing order of a function at a point satisfy. So if I have two functions and they, one of them vanishes to order n and one of them vanishes to order m, then they're going to vanish. Oh, sorry, there's supposed to be a larger then. Then they're going to vanish to at least the minimum of those orders when I take the sum. And when I take the product, the vanishing orders just add. All right, and I didn't finish my sentence here. There exists such a map, nu, such that R is the elements of the fraction field where nu is non-negative, and the maximal ideal is the elements where it's strictly positive. And if I wanted to normalize this properly, I would also say that there exists nu such that an element where nu is 1. Otherwise, you can do dumb things like take a valuation and then multiply it by n. All right. So the way you should think about this is, in this case of a Noetherian ring of dimension 1, it sort of looks like a curve. And if I have a point, I have a notion of whether my function vanishes at that point, or more generally, if I have a rational function, it might have a pole at that point. So if nu of x is equal to n, which is non-negative, that means x vanishes to order n. P. So this is my point P. On the other hand, if this is negative, that means x has a pole. Order minus n. You can check solomorphic functions on C or on the Riemann sphere. If they extend to the Riemann sphere, the orders of vanishing and poles exactly satisfy these rules. And for a rational function, over C, it corresponds to the same notions for thinking of it as a holomorphic function. Yes. K of R is the fraction field. Why is R a domain? I'm saying this is equivalent to all of these properties. So, I mean, I can add R as a domain here. I'm telling you that it's a subring of a field. Well, I'm trying to state all the equivalent characterizations of being a DVR, right? So I could just say there exists a field K, an evaluation on that field such that R is this subring of K. And once I know that, well, I know R is a domain, and I know that actually K has to be the fraction field of R. Right? All right. So, I mean, you might look at this and say, oh, well, that's cool to know about curves. And of course, it's interesting to think about this, for example, for spec of Z, right? In that case, a function on spec of Z is an integer, and it vanishes at a prime if it's divisible by that prime. So its vanishing order is the number of powers of that prime it's divisible by. If I have a rational number, it has a pole at that prime. If, when I put it in least terms, the prime divides the denominator. So this is sort of useful for thinking uniformly about curves over C, curves over a finite field, and spec Z, or more generally spec of the ring of integers of a number field. But this is actually also relevant in a bunch more cases, right? Because even if my scheme X has dimension K, it actually might have a bunch of points where the local ring is regular dimension 1. Right? So even if dim of x is greater than 1, if I take a point p in here with codimension 1, so what does that mean? That means p should be the generic point of a subscheme, an irreducible subscheme of dimension 1. So I can take, A3, and I can take a surface in A3, right? And look at the generic point of that surface, and that's going to give me a point with codimension 1. Then the Kroll dimension, xp is 1. Maybe I'll just say often. And probably that's always true, but I'm already out of time, so let me not evaluate that. That's certainly what you would expect to happen. And it might be regular. So one useful thing about having all of these characterizations is, right, for example, if x is spec of r, or r integrally closed, the x is normal, then this will always happen. So for example, if I'm thinking about my surface in A3, that has a local ring attached to it, which sort of measures what my function does generically on this surface. That's its image in the residue field. And then sort of remembers what happens transversely to this guy, but only generically on the surface. And so in that case, what I'm asking is, when I say vanishes to order n at p, well, that means it vanishes to order n on the whole surface. And when I say to order n, I mean, when I look transversely to the surface, how does it behave? Does it look like a polynomial of degree 1 or a polynomial of degree 2 or a polynomial of degree 3? So this maximal ideal m of xp equals, so what is this? This is functions. Well, it's going to be on an open set containing my point. On open set with dense intersection with the closure of P, right? If I contain the generic point of a closed subset, that means I have dense intersection with it that vanish. So I can say vanish at P, but of course, vanishing is a closed property. So that's the same as saying they vanish on P bar. So, right, this is again one of these points where suddenly it becomes actually really useful that I kept these non-closed points around, where I can talk in a uniform way about what happens at closed points in the local ring there, and am I vanishing there? Or at a non-closed point, at the generic point of some big subscheme, I'm asking, do I vanish along that whole subscheme? And so, for my purposes, what does vanishing to order 2 mean? It means I'm in the square of the maximal ideal in that local ring, right? I know the product of 2 things that vanishes to order at least 2, and the product of 3 things that vanishes to order at least 3, etc. And that's really my definition. All right. And if I look at a rational function on this guy, well, this valuation tells me Does it vanish on this guy? Does it have a pole on this one-dimensional subset, right? If I look at where I am in the fraction field of the local ring, and I'm not in the local ring, that's telling me that I blow up somehow. And we're out of time, but I think the other class doesn't come in, so it's safe to go a minute or two longer. On Fridays. So you should have, from complex analysis, some general notion that functions are holomorphic, like meromorphic functions are holomorphic if they have no poles, right? So what does that mean in algebraic geometry? Well, the replacement for holomorphic is being regular, being an actual honest function on the scheme, right? And now I'm telling you what having no poles means. I would say a function has no poles. Well, let me first say, assume all local rings, ODIM on points are regular. I'm assuming that all the codimension 1 points are regular. What that's measuring is when I take this big subscheme and I smooth sort of transverse to it. So maybe there's some singularity somewhere here. Maybe this guy has a weird kink or it has some crossing over itself. But if I look generically, am I smooth in the transverse direction? So at all ODIM 1 primes, type points, the star f of p is then O xp. And here f is going to be a rational function. And probably I should be assuming here that x is integral. Right, and this is measured by, i.e., the valuation corresponding to this point on f is non-negative. Right, the valuation corresponding to that point tells me, does f have a pole along this codimension 1? And theorem, if x is normal, so if all of the local rings are integrally closed, then f is an honest function, as in O of x, if and only if f has no poles. And this is what Vakiel calls the algebraic Hartog's theorem. Right, Hartog's theorem tells you if you have a holomorphic function in many variables, if it has no poles on submanifolds of codimension 1, then it has no poles. Right, that I can holomorphically extend a function over anything whose codimension, complex codimension, is greater than 1. Right, and this is saying on a normal scheme, that also is true. If something blows up, it blows up generically on something of codimension. Now you sort of see the problem with this. If you look, oh, I deleted this, but if you look at things like C of p squared t cubed, right? So the reason I need normal is exactly something that's in the integral closure of these functions isn't going to have a pole anywhere in this sense, right? If I have something that's in the integral closure, then at any regular codimension 1 prime, at codimension 1 point, it's not going to have any poles because it's going to be in the DVR itself because DVRs are integrally closed. So I really do need this normal property. There are non-normal schemes where this goes very well. All right, great. Yeah. Okay, yeah, what do I, right. I should have said frac of O of XP. Right, what's frac of O of XP? That's the same as K of X. I'm being bad here, right? Like somehow, if I'm on an integral scheme, a rational function just means an element of this fraction field. So what I'm saying is if I take an element of this fraction field, I want to know whether it defines a regular function. What do I need to do? I need to test at every point, does it have a pole or not? But only at codimension 1 points, because those are only the points where it makes sense. Yeah. No. F is in K of X. No, I mean, if I have a rational function, I can still take its stock at a point, but it's not going to be an element of the local ring. It's going to be an element of the fraction field of the local ring, which is just the same as the function field of the variety. Right. So I wasn't being careful about my notation here. There are no stalks in this statement, right? I'm just looking at an element of the fraction field. And I'm saying, well, so that's a function defined on an open subset. And I'm asking, does it extend? How do I check whether it extends over the closed guys I pulled out? And to check that, if X is normal, I only have to check, do I have a pole on a codimension 1? If X is not normal, this can be weirder. There's more sort of complicated stuff going on. All right. Well, I'm way over time, so we'll stop here. Pick up next time.